Thank you very much for the introduction. It has been delightful to be here the last day and today. I think I enjoy every minute of it. It's one of the very best meetings I attend for many long time. So as it turned out in the many talks throughout these meetings, the cryo-EM field has been progressing in the last 10 years in particular. So right now we have more than 10,000 structures, and some of them are only the bottom data. 40% of them have coordinate data equivalent to a crystal structures. And among these, there has been shown in previous speakers in the last few years, there has been a rise in terms of the resolutions coded by colors. In last year, 2019, the major structures at high resolution actually have 3 or 4 angstroms. So I think this is a comfort zone because it's, if you're a good specimen, you can get that quite readily. And I think as you can see that the data at the 2 or 3 angstroms are in the rise as well. So I kind of like to give some historical descriptions of where the community has been working together with people in protein data bank, both in America as well as in Europe. Back in almost 15 years ago, we realized, particularly the PDBE over in Kingston, realized that we need to establish a common vocabulary so that we know we talk about the same currency and same language. So we have our first meeting to define the dictionary, what we call by resolution, map, and coordinate, because for a long time, the crystallographer doesn't understand exactly what we are talking about. Bottom data, we are not talking about atom positions in the old days. And so in the 2010, we actually begin to think about the validation, because at that time, my group was one of the first ones to show we can actually trace the backbone of a polypeptide in a molecular machine. We actually done 2 of them. And so that begin to think about how we validate it as in the crystallographer, decades ago. So, in fact, that meeting was very important because we begin to think about how do we define resolutions. Now, in crystallography, you see the spots, and where the spots end is where the resolution is. If you talk to the traditional microscopy or go to Google, the word resolution, you talk about what is the minimum distance that you can resolve, the Rayleigh criterion based on the optics. Unfortunately, cryo-EM, when we talk about resolution, is neither one of those definitions. So I can't like to just define, it has been used throughout the last couple of days, and I can't like to define it in a minute, what we mean by resolution. And then subsequently, there are numbers of meetings that we have done with not just ourselves, but the entire community, similar to the crystallography. It's not 1 lab or 2 labs. It's actually the global community come into consensus. That's how it's done. So I'll give some report in some of this activity. So based on these discussions, then I'd like to address in the next few minutes about some concept that I like to convey just so that we are all in the same ground level. How do we validate both cryo-EM map and model? Because when we talk about cryo-EM structure, there are 2 data. One is the map, the other the model. Keep in mind, what do we mean by model is a simplistic representation of the density map so we can comprehend. So whatever we show in the model has to look like where the experimental measurement, namely the bottom data. So that's very important to keep that in mind, because I can build a perfect model, perfect geometry, but it doesn't match with the map. So it's very dangerous activity. So I think that's some of the point we point out yesterday, that this perfect geometry, but that has nothing to do with reality. So we want to make sure that the data and the model agree. And then now one of the questions that we have to keep in mind is, once we put up a model deposit in PDB, we pick up the model and we compute the map. Does that map look like the original experimental map or not? The answer, we should be, but sad enough, most of them are not. I just want to bring up that point in a couple of slides. And then the third point is exactly how we deposit the data so that the readers of your data know exactly what kind of accuracy or uncertainty your structures are. And finally, as we pointed out, that in the last year or so, there are more structure at the kind of 2 or 3 angstrom level. That at the regime, that in the kind of gray zones, as Eleanor points out, you really need to go down below better than 2 angstrom to do that. But I think now we are getting a map 2 or 3 angstrom. What can we say about water or metal in addition to the amino acid or nucleic acid bases or sugars or lipid and that kind of stuff? So these are the few points I'd like to cover in the next few minutes. First, let's define what we mean by resolution. As pointed out in some of the previous talks, that in the cryo-EM has in the 2004 meeting, we agree on that we need to, because we don't have so-called R3 as the crystallography, so we can actually collect 2 sets of data. And one set of data, we start with some sets of particle and then create a map, we are called map 1, and other independent sets of data, we generate the map 2. So now has been a tradition in, I would say, more than 98% of the published cryo-EM data have these 2 independent sets. But I would say even today, there's still publication as only 1 data set. I don't know how it gets published, but there are many journals. There are ways to get published anyway. But I think the best practice, we need to have 2 independently determined data sets. And based on that, since we have a 3D volumes, and then we can calculate its Fourier transform. So the resolution we define is called Fourier cell correlations at a threshold. So what the Fourier cell correlation is a dot product of the complex number of the Fourier transform. In other words, the ambident phases of one map with respect to the conjugate of the second map and normalize it. That is how that Fourier cell correlation means. So the resolution is defined in such a way then, because this is a parameter which measures the similarity of 2 volume density, 2 features, okay? And when the similarity is high, that the maximum number is 1, and when they become dissimilar, and that would be 4 down, and at some level that they don't recognize each other, equivalent in your phase residual in crystallography, got random phase. Okay, that is what Richard Henderson had derived with Peter Rosenfeld. This 0.143 criterion would be equivalent to a kind of random phase error in the data. So that is how we define resolutions. Now, as is pointed out in many talks, in the cryo-EM map, the resolution is not uniform throughout the entire volume. So some area are better, some are worse. So what now we are giving is 1 numbers. Now think about 1 number, you grade a student how dangerous it is. It's a kind of good pop-up, but it can be really misleading as well. You see, I'm sure most of the Nobel laureate does not have a 4.0 average in the grade point average, right? But on an average, they are just smart, but because we're parameters. So we need to consider many other factors as well. So now, it turned out when we do the image processing, depends, we haven't talked about it in the last couple of days. There are many ways of doing image processing. You can keep refining in such a way you can push your curve toward the right-hand side. So because you always want to get better numbers. Okay, so that's very dangerous. So one way that we have agreed on is that we want to make sure that we don't refine our map so that make our number look good, okay? So what has been suggested by, again, Richard Henderson is that since you start with 2 data sets, you process it, and then you can also start with the same 2 data sets, and then you can randomize the phase information in each particle at a frequency about 75% what you think your resolutions are. So when you randomize the phase information on your images at that threshold, when you subject your data through the same processing, that means your resolution should not be better than when your phase become random. Okay, so using the same example as I did so, and then the red curve correspond those has been randomized at a claim resolution 3.3 angstroms. That means at that level, using the same data processing scheme, you would get around, in this case, at a low resolution. So that, I think, ensure yourself that you are not over-refining your map or not over-claiming what resolution is. Now, in a sense, I criticize, I comment on the one number is no good. But on the other hand, we need some currency to talk about when we say certain resolution, with some expectation what feature you can see as being pointed out this morning, what you can see as certain resolutions. Now, so since now you have two maps and two reconstructions, then we build model. So at these kinds of free-ish enzyme resolution, oftentimes you can actually trace the polypeptide backbones of many polypeptides in your molecular machine. In this particular case, it's a virus. So since we have two maps, we can build the model of the one of the molecular components, and from there we can compute that model compared to the map. So that means this, again, we can calculate the Fourier cell correlations of the computer map from the model with respect to the raw map. So again, there should be high similarity at low frequency, and then it will fall at high frequency. Again, in this case, it's around 3.4 or 3.3 angstroms. And then with this model, we can compare with the other map, which the model has never seen before. Then we can compute another Fourier cell correlation in the red curve. So you can see if these two data sets are done properly, one model would compare favorably with the map from another data set. So, and then also we can compute what the another model from the second set of data, and then so you have two models, and then we can compare that two models as well. And now, since now we have two models from two independent maps, we can compute the root mean square deviation of all the atom positions, particularly in the C alpha positions, and then you can see how deviated they are. In this case, it's a virus. One asymmetric unit in this case has 7 polypeptides, so we can actually compute not only each of these polypeptides, but also we can refine the model with the whole asymmetric unit, and then we find that in the N-terminals of the two models actually deviate, because that turned out to be a very floppy end of the molecule. And then you can see the two models overlap well with the density in many parts, except at the loop part and then at the terminal part. So I think this is how we define resolution, how we validate the model with respect to map. Now, so then you're happy, and then you deposit in PDB. So you deposit the map in the EMDB. Right now we have one depth, so you can deposit the same site. This I show you only one helix in this molecule. And then from here, you have to add the model as well. Now when you build this model, you actually build model with all the atoms, right? Even though you don't see some of the density, but you still build the atom, lysine or aspartic acid, you build all the atoms. Now, and then you deposit in PDB. When you deposit it, if you pick up that from the PDB, you calculate the map from that model, what do you get? You get this. You get this. Now, when you compare this model-derived map with the experimental map, they do different, right? So some density don't have the density in the original map, and now in your model you have that. So that means whatever you deposit in the PDB is not a faithful representation where your data are. Now, how do you fix that? The way to do this is you can compute the atomic displacement parameter that Paul Adam called is basically the B factor. In such a way, every atom, you can have an atomic displacement parameter in such a way that when you deposit, you are not just deposit the model with 0 B factor, but you have the parameter in such a way that you include it in the PDB deposition. When you do that, then you use this information to compute the density map, and that is what you get, okay? So that computed map does look like the experimental map. So I think that is lesson 1 that I promote to the community that we really need when we present the model. We really need to have a proper atomic displacement parameter in such a way that when we compute the map, we do have a description that do like your experimental data. Now, with this proper weighting with the atomic displacement parameter, we can compute the correlation at each residue level. So this is the correlations between the computed density and the original density at a residue number. You can see in the dark curve represent that the correlation is on an average better than 0.95. But if you don't include the atomic displacement around, the correlation is much poorer. And then when you compute the Fourier cell correlation with the weighting one is much better as well. So that is pretty much that what many of us believe that we need to deposit when we have an atomic model along with the cryo-EM structures. Now, a few years ago, about 5 years ago, there has been so-called resolution revolutions that it's not only a few labs can do it, but many labs can do it because the advancements of the optics and the detectors. So we decided, I and Helen Berman at the RCSB in Rutgers, and also Arden Perwarden over in EBI, we decided we need to get the whole community to do an experiment, as what Kelvin talked about yesterday. You know, which model building is better, or which image reconstruction is better. So our model is not to do it ourselves. We need the community to do it, and then we have the community to judge what they think is good or bad, or what is deficient. So we come up with a benchmark data that we started with some raw images. Again, thanks to Empire that in the EBI that they have the raw images archival. We have 6, 7 different structure have been processed and deposited. We have the raw images, and we tell the community, yeah, get me the map. Can you do better or worse from what is being published in journal as well as being deposited in EMDB. We also give the map to the community, say, can you build a better model than what has been deposited in PDB? So we initially, I thought the community of the image processor and this community modeler, I thought they would not talk to each other, but that was true many years ago, because everybody is dealing how you build the model from the map, or how you get from the images to the model. So we have 2 committees and two panel of judges to do that. And then, so it took a number of years, a couple of years, and eventually we met at Stanford with more than 80 people that some of you are actually in the audience. We have all the modeling major group in CCP4, Phoenix, Rosetta, and Coot, and so on and so forth. They were all invited to make a analysis with more than 100 depositions. And so, and as a result, we also wrote a paper. There are 18 papers I recommend for those of you who want to engage in the details to see how different people doing the image reconstruction, how different people did the modeling. So in a nutshell of all this, it can be summarized as follows in the challenge activity, that the challenge were able to correlate trace significant portions of the benchmarks. Okay, no problem. And in some cases, they made substantial improvement from what was published. That's progress. That's a good news. Okay, and that's about the modeling. But in the conclusion, we also find there are some deficiencies in terms of how we judge according to a single number, the FFC or the correlations. We think that we need to have maybe a combination of the score or different parameter to judge the quality of your structures. And then at that time, the modeler find out that they need to talk to the guy who compute the map, because garbage in, garbage out, right? So they think they need to have some assessment how good their maps are. And then the map guy discovered, how do I judge my map is good? We really need to look at the model, whether that makes sense or not. So I think through this meeting, we discovered that we need to, this is time to merge both community between the image processor people and also the modeling people. And since then, we decided that is 7 or 8 different benchmark data for the community to do, and it took a long time. So we decided last year we did only a few, and we also decided let's look at some really high resolution data, because it turned out at lower the resolution, the harder to judge exactly what criteria, because we want to use the best practice that that many of you have done in many decades. And then so we decided we want to restrict ourselves to some relatively high resolution data between 3 angstroms to 1.8 angstroms. So these are the apoferritin data and also the and one of the enzymes. So you can see that these 1.8 angstrom, those density are quite respectable. And so I kind of like to go on, focus on some of the work we did, and these kinds are better than 2 angstrom. How do we assess it? Okay. And so, we use our microscopes to collect a set of data. It turned out now you have a good specimen, you can collect the data pretty quickly. So this is the apoferritins. We collect 70,000 particles, only 6 hours data collection is done. And a couple hours you can actually generate map according to the Fourier cell correlation is 1.75 angstroms. And then there's a 4 helix bundles, and it's actually quite nicely. The aromatic rings look like a American donut, and then if a lower resolution, you look like a pancake you ate this morning. So now at this resolution, so this was done in our lab. One of the questions that was curious to me is, since this is a technology that now become very popular, that's high demand, the question is, can different labs using different instruments, different software can generate the same quality map? So it turned out last year there's a few labs using this apoferritin, which the crystal structure is known, and they did independently. So here the next slide shows about a few residues that I extracted from several microscopes and different labs. So that the best one now is this 1.54 angstrom, 2 decimal nowadays. So you can see that the reassuring thing is all this density. I just pick up a few examples yesterday in different lab, different specimen, the same molecule, but prepared in different lab and different data collections by different people and different software. They basically provide the same quality of the map, and the model I put in here, because we're X-ray model, we can easily just put it in there. Now, one interesting thing, as Garrett points out yesterday, that in some of these negative charge residue, and at this kind of lower resolution, the density does not show up. So he pointed out there are multiple reasons. Can be the charge repulsion between electron and negative atoms, or it can be radiation damage. It can be a highly flexible. So a combination of 3 above. So now, since we have this, one thing that triggered us to think about how we compare this, we need to we decided we develop a parameter to measure the term I call resolvability. In other words, how resolved it is on each of these atoms. So we, Greg Pintari in our group, that suggests to use a parameter he called Q factor, which basically is a cross correlation between a Gaussian function of an individual atom with the density you think where your atom is. Okay, so, and we call a Q parameter. And then, so when we look at these Q parameters, we can measure it across different atoms in the amino acids, or we can average it according to the clusters of atoms. So these purple color numbers are the Q factor. The maximum number of that is equal to 1. So at high resolution, they're really high Q factor. At low resolution is lower Q factors. And so it turned out this Q factor is also related to a function of resolutions as well. We went to the protein data bank, picked up 50 structures, higher Q factor at better resolution, lower Q factor at poor resolutions. And it turned out the Q factor measure not only the resolvability of the density, but also depend on how good your maps are. So here is demonstrate that we begin to pick up the water molecule in red, and then the green one are the metal ions. And so we turn out that after we refine the model better, because feeding the X-ray is not necessarily the correct way in the EM map. So based on that, the Q factor actually improved after we feed the map better. And then I just want to show one more slide to demonstrate that again, the resolvability in different map, and this is an X-ray map. So they have a metal atom. We do see all the metal atoms. And then the red ones are the water, and these are really good water in here. But interesting in this case, this particular metal atom in this particular case does not show up as good. So by and large, all the metal and water agree well between most of the map, most part of the density. Now, these are the protein. In addition, we actually try out the nucleic acids. It seems to follow the same trend. Is the Q factor also a function of the resolution as well? So we recently have a new density map on the RNA alone. In other words, not RNA and protein. There are plenty of them in ribosome, but this is only naked RNA. In ribozymes, though we are able to get a free angstrom resolution, we actually able to resolve a number of these metals quite nicely. And again, how can we be sure? Because we measure not only the Q score, but also the distances between the metal and also the protein density. So I think the Q score in this case are exactly what we expected from our combinations. So I think this few slides, in the last few slides, I described is the parameters that we think is useful to describe the resolvability of these between 1.5 and 2.5 angstrom resolutions. And as I pointed out, it is important to have the proper parameters to describe your map and model, and then with the statistical definition, not only the whole structure, but at every individual atom, we are reaching to that state. And finally, I'd like to acknowledge the people that who carry the work, and in particular, Greg Pintardi carry out most of the development on the modeling, and the number of people in the lab that involve the data processing. And this collaborative project that we have different colleagues, John King, like the virus one, Das on the RNA, and then we work very closely with Paul Adams. We were the first one to work with him to develop this. They implement this real space refinement for the EM modeling, and with Helen and Kathy in Rutgers, and we appreciate very much to work with Arden and Gerard in the PDBE, and also Andy in compiling this. Thanks very much.
Hello. Yeah, thank you, Wah, for that really nice introduction to state-of-the-art validation for cryo-EM. We have time for a couple of questions. Has anyone got questions? Here we are. Microphones?
Yeah, fantastic. I'm trying to understand the effects of, after having seen the other talk from Gareth and yours now, of damage that we really see in these electron density maps, or charge effects. And now you have metals as well. Could you comment on is this dominated by charge effects?
My interpretation will be the charge effect. okay, because when we get to the one of the slides I didn't show, that we compile all the aspartic acid in the apoferritin, okay, and then do a different, and then when we average all the aspartic acid at low resolution, always the carboxyl group, the density don't show up at 3 angstrom map, but at one better than 2 angstrom, they always are there. So that suggests to me it cannot be a damage effect because they're basically the same dose anyway. But you know, the complexity is they can be flexible, so it's hard to pin it down. But what Gareb suggests is a good one. You know, you need to do more. I think beyond apoferritin now we begin to look more. We're also looking at the damage effect in nucleic acid. There have been suggestions that nucleic acid have different radiation sensitivity because the base, because all these aromatic, yeah. Huh? Metals? Yeah, metals too, yeah.
Okay, we've got another question over here.
So, lovely talk.
Thank you.
But was I correct in thinking, or seeing from over here, that where you had the increasing resolution on the maps, that the missing residues like the carboxyl seem to look much better in your higher resolution data?
Right.
Is that just an artifact, or is it just...
No. As I point out, with all these negatively charged residues at high resolution, they do show up. And in fact, there's some microelectron diffraction data. They have something better than 1 angstrom. And then all those aspartic acids and other things do show up. So that's more point towards Gareb showing a curve on the scattering because a negatively charged atoms and the electron, they repulse, right? And so as a result, at low frequency, they actually have negative density and it causes to positive density. And so, but I mean, that's a known, known facts in terms of scattering.
Okay, one last from Isabel.
I would like to ask, when you are talking about maps, whether there's any standard procedure these maps have gone to. So when you say maps, it is a sharpened map, or is it, what would be the normal map you're referring to? And the other thing is, when you refer to B factors for something like, for instance, apoferritin, is the relationship, the distribution of the B factors for your cryo-EM structure, how does that compare with what the relative ones are for the crystallographic structure?
Yeah, okay. So the first question, do we sharpen the map? We normally do because one of the things nobody has discussed yet, because in images, every images are convoluted with we call transfer functions, which depends on all the optics parameters. So one of the consequences of that is a damping functions. So at high frequency, those are lower. So you really need to jib that up, either jib up the high frequency or lower the low frequency information. That's what the sharpening does. And so this has to be optimized. So we actually have done many years ago to plot this sharpening factor, equivalent to the B factor, mathematically speaking, that depends on the numbers of particles as well. So you can always compute your map with different numbers of particles. Smaller numbers of particles, then you have a lower resolutions, which means the damping factor, the B factor is higher. Okay, so do I answer your question? Maybe only partially.
Well, yes, it was two questions. So the first, yes, but I was curious because you were talking about fitting the B factors, how this compared for a structure like apoferritin with the distribution of B factors that this same structure has in the X-ray determination.
Yeah, I think the thing is all the map that by the cryo-EM, I don't think anyone except us to redo the modeling. I mean, they just deposit the map because that's what they did, just to claim they could do it, right? And so I think in order to do it, in fact, interesting, there are many apoferritin X-ray data. We talked to Paul Adam. He thinks he can use now with the new technique to refine the old X-ray data that can do better as well. So that in doing all this comparison, I think you need to be critically look at that.
Okay, thanks for answering that. Time to move on for the next speaker, which is John.